Number 21, which of the following compounds will readily lose carbon dioxide when heated? Well, this is called decarboxylation, and that occurs only when the carboxy group is bonded to the alpha carbon of another carbonyl. For example, here we have a carboxy group bonded to the alpha carbon of another carbonyl. So this is a yes. This will readily lose carbon dioxide. Now here we have a carboxy group, but it is not bonded to the alpha carbon of another carbonyl. It is bonded to the beta carbon. So this will not lose carbon dioxide. Here is a carbonyl, and here is the alpha carbon, and we have a carboxy group bonded to that alpha carbon. So this is a yes. Here is our carbonyl, and here is our alpha carbon. Here is beta carbon, and here's our carbonyl. So this will not lose carbon dioxide. Number 22, draw the products of each reaction. So we're working with some malonic esters. So here, I'm just going to draw this a little bit differently so that you can see those esters. And we're working with the same compounds here. So the first step actually deprotonates. So we will remove one of these acidic hydrogens. So I'm just going to erase it here. Now we have a carbanion. So then this bromine here, this alkyl bromide, can come in and attach. Now we're going to undergo hydrolysis and decarboxylation. So first, the hydrolysis, the ethyls are removed, and this becomes a carboxylic acid. Now we look to see, can we take away carbon dioxide? And the answer is yes, because we have a carboxyl group attached to the alpha carbon of another carboxyl group. So I'm going to erase this one. That's removed, and give this carbon a hydrogen back. So this is actually the product of this reaction. So for B, we're going to go through the same steps. I'm going to draw it like this. And go through the same steps. The first step is to remove the acidic hydrogen. Then the alkylation comes in. So here's the alkyl. Then we're going to do it again. So here this hydrogen is removed, and we're going to put in another alkyl group. Then we're going to hydrolyze the ester. So these become carboxylic acids, and then check for decarboxylation. Here we have a carboxy group that is alpha to another carbonyl, so I'm going to remove that, give him back an H, and this is the product of this reaction. Number 23, what cyclic product is formed from each dihalide using the malonic ester synthesis? Well, it might be easier to see this. This is going to be an intramolecular malonic ester synthesis. I'm going to draw it like this. There's 1, 2, 3. That's one too many here. We need, there's our chlorine. And so then we need our malonic ester. So we're going to start with this here because I think we know how to make the ion at this point. So here, this carbanion is going to come after our vulnerable carbon, and that's going to kick chlorine off. So then we're going to end up like this. Now, and sodium bromide, or chloride, not bromide, sodium chloride. So now, with some more ethoxide, then we can go after, because this is going to end up we're going to remove this acidic proton here, and I'm just going to erase just to save a little time and messiness. And so we form this as our new anion. So this is going to come after here and remove this chlorine. So let's count. We have 1, 2, 3, 4 carbons now that are going to join in a ring. And we still have our esters. Then we're going to go with the last step, hydrolysis and decarboxylation. So first things first, we're going to remove these ethyls and replace them with hydrogens. That's our hydrolysis. And then our decarboxylation, where one of these gets removed entirely. So that will be our product for A. For B, let's see, this is A. For B, we have an ether. A similar mechanism is going to occur, so I'm just going to start with my ester ion like this. This comes after this vulnerable carbon here, which kicks the bromine off. And then we have our acidic hydrogen. So that acidic hydrogen gets removed. Here we go. And then I'm going to swing this around a little bit, make this a little easier to see how the intramolecular reaction would occur. There we go. So that's going to come after here. And then we form a new ring. We still have our ester groups. And the last step, hydrolysis and decarboxylation. First, the ethyls are removed. Then we decarboxylate, and we have our product. Number 24, what alkyl halides are needed to prepare each carboxylic acid to the malonic ester synthesis? Well, in order to find that, start by binding the alpha carbon to the carbonyl. So my alpha carbon is here, my alpha carbon is here, my alpha carbon is here. Now, everything that is basically bonded to that alpha carbon were alkyl groups that had to be brought in. Everything else is from the diethyl malonate. So here we would use all of this with, I'm just going to give it a bromine, with a bromine. That would be the alkyl halide needed. Here we have two groups. So we would have a propyl and this group. And here we would have two butanol groups. So this would be butyl bromide. And number 25, explain why each of the following carboxylic acids cannot be prepared by a malonic ester synthesis. Well, this reaction, the malonic ester synthesis, works best when the alkyl halide is primary or methyl halide. That's because we're working with an SN2 reaction mechanism. Here we have a tertiary, this part right here is a tertiary alkyl, and so a tertiary alkyl halide is just too crowded for an SN2. And here's our carbonyl, here's our alpha, so here's the remainder, and we're looking at an aryl halide as a leaving group. Aryl halides are unreactive in SN2 reactions. And here's our carboxyl, and here's our alpha, so we're looking at everything next door. So we have three methyl groups and the 3 methyl groups on the alpha carbon. So the malonic ester synthesis can be used to prepare mono and disubstituted carboxylic acids, but not trisubstituted.